Welcome to this lecture where we're going to talk about working with functions. The purpose of this lecture is to talk about some shortcuts for analyzing the growth of different functions, including composing different functions together, using limits, and the specific use of limits with L'Hopital's rule. So the first thing that we want to talk about is, suppose that we have two algorithms, algorithm A1 and A2, and they have running times T1 and T2, which are upper bounded by f of n and g of n, respectively. So algorithm A1 is big O of f of n, algorithm A2 is big O of g of n. Then suppose that we have the running time of the two of them together added. T1 plus T2 is equal to big O of f plus g of n. Or perhaps if one dominates the other, the max of f or g of n, the larger of the two. And what this means is, why would we add these together? This happens whenever we run A1 and then we run A2. So you have two different algorithms. You run the first one, you run the second one. The total time is the sum of both of them. And the point here is that the analysis can be combined in the same way. We can add the f and g together, or if we're looking for just the largest term, which we often are, we can take the max of whichever those two is largest. Okay, so this is a natural thing because we often take two algorithms and then run them side by side, one after the other sequentially. On another hand, what if we ended up with a runtime that is T1 of n times T2 of n? Well, then we would just multiply together f times g. And this would occur anytime that, say, A1 uses A2 at each step. So every single step that A1 does calls A2. And this could be because of nested loops or function calls. For example, every step that A1 does is a function call to A2. Okay. And this again occurs naturally in these kinds of contexts. We often see nested loops and this sort of thing. So we can combine the analysis of different running times just by adding or multiplying them together, depending on if we're running them sequentially or they're calling each other. Other useful facts, suppose that our t of n is a polynomial of degree k, so something like, n to the third, okay? Then t of n is equal to big theta of n to the k, so that would be, in this case, n cubed, okay? Another fact is log to the k of n, which is just shorthand for this notation right here. In other words, log of n to the quantity to the power k. So this k here is just a shorthand for this, is equal to big O of n for any constant k. So it doesn't matter if k is 10 or 100 or 1,000. For example, log to the power, 1,000 of n is equal to big O of n. So for any constant k, and that's important here, the k must be constant. We're not talking about log to the power n of n. We're talking about log to the power k. And the whole point of saying this, you might wonder why we're talking about this, is to point out that logarithms grow very slowly, even if you raise them to very large powers. And we'll prove this statement shortly. But before we prove it, let's introduce one more tool into our toolbox. Sometimes limits can be very helpful when we're trying to determine which two functions grows more quickly. So if we have an f of n and a g of n, and we don't know exactly which of them grows more quickly, and we're trying to determine that, oftentimes we can just determine it by looking at it, but sometimes we can't, and then limits become useful. So if we take the limit as n goes to infinity of the ratio f of n over g of n, that limit must be one of essentially three different types of values. If the value of this limit as n goes to infinity is 0, well, if this is equal to 0, as we say here, then that means that g must be growing much faster than f, because this gets much larger than this, and therefore the ratio becomes 0. And in that case, then we can say that f of n is strictly upper bounded, little o. We could also say big O, but a stronger statement is to say that it's strictly upper bounded by g of n. G of n grows strictly quicker than f as n increases, okay? So that's category one. This limit might be equal to 0. Another category might be that it's equal to some constant c, which is not 0, so like 5 or 10 or 100. Okay, if the limit as n goes to infinity is equal to, say, 100, for any, that means that f is growing at a rate that's 100 times of g, but that 100 times is constant. So and we ignore constant differences when we're doing analysis. So what that means is that f of n and g of n are growing at the same rate, which means that f of n is equal to big theta of g of n. Or we could have expressed this the other way around. We could have said g of n is equal to big theta of f of n. Okay, so that's if this limit is equal to a constant, which is not 0. And the third category is that this limit goes to infinity. So f over g goes to infinity, which means that f is getting large more quickly than g is getting large, and f is growing faster than g. Okay, and in that case, we just sort of reverse what we set up here. We can say g of n is equal to little o of f of n. F of n is growing strictly faster than g of n. Okay, so limits help us there if we can take the limit. Now, sometimes we can't take the limit directly, and in that case, L'Hopital's rule is useful, which you may remember from classes in calculus. L'Hopital's rule says that kind of amazingly, that the limit of a ratio, f over g, is equal to the limit of the derivative of f divided by the derivative of g. And the amazing thing is that we can take these derivatives separately, right, independently of one another. So if I had the limit, just give you an example, if I had the limit of, n cubed over the log of n, right? I don't know what that limit is necessarily, but I could replace this with 3n squared, which is the derivative with respect to n, and I could replace this with 1 over n if it's the natural log, and then I'm left with 3n squared over 1 over n, which is equal to 3n cubed, right? And that's equal to the same value as the original limit. And I know what that limit is. That limit as n goes to infinity is, of course, infinity. So I can determine the value of this limit using L'Hopital's rule. Now let's apply L'Hopital's rule to find the relationship that we mentioned earlier between the power log to the power k of n and n. We said that log to the k of n is equal to big O of n, but let's see why that's true. Let's define capital L as this limit. And here we've put in the numerator log k of n, and the denominator n. So these are the two terms or two functions that we're working with, and we want to know that limit as n goes to infinity. Now, this limit is not immediately clear. What is the relationship between log k of n and n? We don't know. But one thing we can do is we can look at the derivatives of these two things separately, right? The derivative of this is just 1, and the derivative of this is written down here. This is k, because remember, log k of n is log of n to the power k. So we can take that k down, and we get k here, log to the power k minus 1 of n, and then we have to take the derivative of this inner portion, which gives us 1 over n, like we saw before. Okay, so we know that this is the derivative of the numerator, and the derivative of the denominator is very simple to take, so we could apply that. Okay, and so that's what we do. L is this. Well, it's also equal to this, right? This is the derivative of the numerator that we just showed up here, and this is the derivative of the denominator, like we just mentioned. And then we could bring this this n down here, and we're left with this. And look, this looks similar to what we started with, right? K times log k minus 1 of n over n is similar to log k of n, okay? I don't know what this limit is either, but you know what we can do? We can apply L'Hopital's rule again, right? And if we apply L'Hopital's rule again to sort of this portion and this, and what we're going to be left with is we're going to have k, remember that was from the first derivative, times k minus 1 from the second derivative of log to the power k minus 2 of n over n divided by 1 again, which gives us k times k minus 1 times log k to the power k minus 2 of n all over n. Okay, but I still don't know what this limit is. So what do? Take L'Hopital's rule again, of course. And then we're left with k times k minus 1 times k minus 2 of log to the power k minus 3 of n divided by 1, which is equal to this. Great. But I still don't know what this limit is. Okay, so will this process that I'm suggesting that we take L'Hopital's rule over and over and over again, will it ever end? And the answer is actually yes, it will end. And why will it end? Well, because every time we do this, notice that we're reducing the power in this exponent by 1 every time we take the derivative. And remember that according to our earlier definition, k is a constant. And so we can only remove k, we can only do this k times before we get down to log to the power 0 of n, which is essentially equal to 1, right? And so the n essentially goes away because that's log of n to the power 0. Okay, so eventually we're going to get to k times k minus 1 times k minus 2 times k minus 3, etc., which is equal to k factorial times log to the power 0 of n divided by n, which is this. Okay, now k factorial is a large number, but k is a constant, and so k factorial, even though it's a large number, is still a constant. And what is n doing? It's going to infinity. So this value is equal to 0, right? Because as n goes to infinity, it certainly is going to be larger than k factorial, even though that's a very large number potentially. So according to the limit rules that we talked about earlier, log to the power k of n is equal to little o of n, which is what we stated earlier. But when we stated it earlier, we used big O. So this is actually a stronger statement. So all these tools you should have in your toolbox so that if you look at two functions that you want to analyze and you don't know which one's growing faster, you can apply limits, you can apply L'Hopital's rule, and of course, simpler things like knowing about polynomial growth and the addition and multiplication of different runtimes. Okay, so use those going forward.